Good day, class, and welcome to another lesson of organic chemistry. Hope you've been enjoying your lesson so far. In our previous lessons, we started treating hydrocarbons, and we said hydrocarbons are compounds containing carbon and hydrogen only. And we also said there are basically two main types of hydrocarbons, that is, aliphatic hydrocarbons and aromatic hydrocarbons. We said aliphatic hydrocarbons are straight chain hydrocarbons, that is, compounds in which the carbon atoms are arranged in a straight chain. We went further to say aromatic hydrocarbons are compounds in which the carbon atoms are arranged in a ring structure. In our previous lessons, we started treating aliphatic hydrocarbons, where we started with alkanes, and we said alkanes have the general molecular formula CnH2n+2, and that each carbon atom in alkanes are sp3 hybridized and thus are tetrahedrally surrounded by hydrogen and other carbon atoms. We said alkanes have single bonds between carbon atoms, and down to the isomerism in alkanes, we said alkanes undergo structural isomerism, whereby it gives rise to either chain or branched isomers. Okay, we went further to see the sources of alkanes, and we said industrially the main source of alkanes, that is the main sources of alkanes industrially, can you obtain alkanes from the industry? The main sources are by fractional distillation of crude oil and by destructive distillation of coal and natural gas. From the laboratory, we said we could obtain alkanes, and the main method, the most important method of obtaining alkanes from the laboratory is by hydrogenation of alkenes. And hydrogenation of alkenes means addition of hydrogen to alkenes. We went further to see that we could also obtain alkanes from the industry, rather from the laboratory, by reduction of halogenoalkanes. And we said halogenoalkanes can be reduced by word synthesis, can also be reduced using nascent hydrogen, and also by using a Grignard reagent. We also said we could obtain alkanes from the laboratory by decarboxylation, that is removal of carbon dioxide from a sodium salt of carboxylic acid or carboxylic acid with soda lime. And we said soda lime is a mixture of sodium hydroxide and calcium oxide. Next lesson we did the physical properties of alkanes, like I told you earlier, and we said down the group what influences these physical properties is increase in van der Waals forces as the molecules get bigger. Thus, from up to down, that is from top to bottom, we have methane as the first compound there, and this compound is the first, CH4. Descending the series, that is from CH4, which is methane, down the group, their melting and boiling point increases with increasing relative molecular mass. And this increase in relative molecular mass is due to increase in van der Waals forces down the series. Thus, this van der Waals forces influences the melting and boiling point of alkanes. We also said the gases and liquids are all colorless with variation in their melting and boiling points. We said the alkanes change from gases to liquids and then to solids. We went further to see the reactions of alkanes, where we said the alkanes undergo two main types of reactions, that is substitution and combustion reaction. And then the last thing we did under alkanes was cycloalkanes, where we said cycloalkanes are saturated hydrocarbons where the carbon atoms are arranged to form rings. And we compared cycloalkanes with their corresponding alkanes. We said that cycloalkanes have a higher boiling and melting point and are slightly denser than their corresponding alkanes. For example, if you have to compare cyclopropane and propane, you see that cyclopropane has a higher boiling point than propane, and cyclopropane has a higher density than propane. We saw the types of reactions cycloalkanes undergo, and we said they undergo mainly addition reactions to form alkanes or substituted alkanes or alkyl compounds. And for our lesson today, we are going to be treating alkenes. Alkenes is a second class of aliphatic hydrocarbons. Alkenes are also straight chain hydrocarbons. That is, they are one type of aliphatic hydrocarbons. And what are these alkenes? What are they like? Alkenes have multiple bonds between carbon atoms. They have the general molecular formula CnH2n plus 2. Alkenes are straight chain unsaturated hydrocarbons with general formula CnH2n. The unsaturated carbons are sp2 hybridized, whereby they are attached to each other by one sigma bond and one pi bond. They form a homologous series of unsaturated hydrocarbons. They contain carbon-to-carbon double bonds and have a general molecular formula CnH2n. The unsaturated carbons are sp2 hybridized and are attached to each other by one sigma bond and one pi bond. The pi electrons are much more exposed than those of the sigma bonds, making the pi bonds more vulnerable to any attacking species. What we mean here is, since the pi electrons of the pi bonds are more exposed, we realize that as they are more exposed, if alkenes have to undergo a reaction, we realize that these pi bonds will first of all react before the sigma bonds can react, which thus says that the pi bonds are more vulnerable to any attacking species. Alkenes are generally more reactive than alkanes due to the presence of carbon-to-carbon double bonds in alkenes. The next subheading we are going to look at there is isomerism in alkenes. The next subheading, like I said, we're going to look at is isomerism in alkenes. Alkenes undergo two types of isomerism, that is structural isomerism and stereoisomerism. The structural isomerism is position and chain isomerism. Position isomerism refers to the position of the double bond, while chain isomerism is due to the branching of the hydrocarbon chain. They undergo both structural and stereoisomerism. The structural isomerism present in alkenes is position and chain isomerisms. Let's look at the examples there. The first one we're going to look at is butene. You can see the various structures there. The first one showing but1-ene, and the second one showing but2-ene. The third one is showing 2-methylpropene or isobutene. Okay, if you realize now, you see that, take a keen look on your screen, you see that the isomers 1 and 2 are position isomers, whereby at 1, that's Roman figure 1, the double bond is at carbon 1, and at Roman figure 2, that's the isomer Roman figure 2, the double bond is at carbon 2. Then you go further to see that the isomers 1 and 3 are chain isomers. 1 is a straight chain isomer and 3 is a branch chain, straight chain isomer. Like I earlier said, if you look at the isomers 1 and 3, they are chain isomers, whereby the isomer 1 is a straight chain isomer and isomer 3 is a branched chain isomer. Meaning here that what? If you see a methyl group is being attached on the second carbon atom, that is, I'm talking on the isomer Roman figure 3. That methyl group gives rise, as it is attached on the second carbon atom, it gives rise to the name of the compound as 2-methylpropene. The longest chain there is 3 carbon, and 3 carbon refers to pro, that is propene in this case, because it is an alkene. One and 2 are position isomers. 1 and 3 are chain isomers. The stereoisomerism present in alkenes is geometric isomerism. For example, take an example there. We're going to see that if you take a keen look on the board there, you see trans-butene and cis-butene. The stereoisomerism alkenes exhibit is geometric isomerism, like I earlier said, which results to trans and cis isomers. Trans isomers result when same atoms or same group of atoms lie on opposite planes. While with the cis isomer, same atoms or same group of atoms lie on same plane or same direction. As you can see from the example on the board, trans-butene, that is the first one on your left, trans-butene, the methyl group and hydrogen atoms lie on opposite planes, while the cis-butene, the methyl group and hydrogen lie on same plane. The next thing we are going to look at is how we can obtain alkenes, that is, preparation of alkenes. Most alkenes are obtained industrially by cracking of higher petroleum fractions. For example, we have there C10H22, which is going to give rise to C4H8. C4H8 is butene and C6H14. These two, one is an alkene, which is butene is an alkene, and the next one, C6H14 hexane, is an alkane. The next example that we're going to look at is ethane undergoing cracking. Is going to give us ethene plus hydrogen gas given off. Next one is propane undergoing cracking to give us ethene plus methane. In the lab, alkenes are obtained by 1. Dehydration of alcohols. Dehydration means removal of water, and in this case, removal of water from alcohol to yield alkenes. Dehydration of alcohol with concentrated sulfuric acid at 180 degrees Celsius is known as a complete dehydration. Meanwhile, dehydration of alcohols with hot aluminum oxide catalyst at 350 degrees Celsius is known as partial or incomplete dehydration. When alcohols have been dehydrated, they result to alkenes. The main product, the end product is an alkene. Heat an alcohol with excess concentrated sulfuric acid at 180 degrees Celsius. This is a complete dehydration, like I earlier said. We have there ethanol in the presence of concentrated sulfuric acid is going to give us ethene plus water. Pass vapor of alcohol over hot aluminum oxide catalyst at 350 degrees Celsius. This is another dehydration reaction. I said this one, whereby it is hot aluminum oxide catalyst used at 350 degrees Celsius. This one is incomplete dehydration. Like you can see from below, ethanol still undergoing dehydration in the presence of aluminum oxide catalyst at 350 degrees Celsius is going to yield us ethene plus water. The second process there, second method by which we can obtain alkenes is by dehydrohalogenation of halogenoalkanes. Dehydrohalogenation means removal of hydrogen halide from halogenoalkanes. And this removal of hydrogen halides from halogenoalkanes takes place in the presence of concentrated potassium hydroxide and alcohol under reflux. Under reflux means heating in a container. Look at the example. We have bromoethane undergoing dehydrohalogenation in the presence of concentrated sulfuric acid and alcohol to give us ethene. And that's it. Ethene plus hydrogen bromide. The next subheading we're going to look at is physical properties of alkenes. They are insoluble in water, but soluble in organic solvents. The first three members of alkenes are gases, that is carbon 2 to carbon 4. From carbon 5 to carbon 15 are liquids, while above carbon 15 are solids at RTP, that is at room temperature and pressure. Their boiling points are slightly lower than those of their corresponding alkenes. What we mean here is this. We say their boiling points are slightly lower than those of their corresponding alkenes, meaning that alkenes have a higher boiling point than their corresponding alkenes. Meaning, if we want to compare, we're going to compare ethane and ethene. Ethane has a higher boiling point than ethene. Propane has a higher boiling point than propene. Butane has a higher boiling point than butene. Next, we are going to look at its reactions of alkenes. Due to the presence of the pi electrons, the reactions of alkenes are characterized by electrophilic addition. The reactions of alkenes are characterized by electrophilic addition across the double bond. This addition would either be ionic or free radical. The first reaction type of alkenes there is addition of halogens, that is halogenation. This takes place, halogenation of alkenes takes place in the presence of ethanoic acid at RTP, at room temperature and pressure, and in the absence of light. If light is present, free radical addition takes place. What we mean here is this. We mean that for the halogenation of alkenes to take place successfully, it needs to take place in the absence of light, but in the presence of ethanoic acid and at room temperature. If light is being present, then instead of addition reaction, it's going to be a free radical addition, whereby this light is going to form free radicals. You can see from the example there, we have ethene reacting with bromine. If you look keenly on the board, you find that there's an arrow moving from the double bond of ethene to bromine, and bromine has reacting species. That is the positive and the negative sign. Bromine is having a dipole moment. And you can see, bromine has been divided. That is, we earlier said bromine, all the halogens are diatomic molecules. And as such, they'll be hydrolyzed to give us at dipole moments the reacting species, electronic species. And there you see a bromine with a positive sign and a bromine with a negative sign. Note that an arrow moves from the negative to the positive, and a double bond, a multiple bond, be it a triple bond, a double bond, a quadruple, whatsoever, in as much as it is a multiple bond, it represents a negative charge. Therefore, we find our arrow moving from the double bond of ethene to the positive bromide ion, and it is going to yield us, at the end of the day, we are going to have 1,2-dibromoethane. 1,2-dibromoethane. You see that from our 1,2-dibromoethane, as you can see there, you find that when ethene reacts with the first bromide ion, it's going to make one of the carbon atoms to form a positive ion, giving rise to the carbon atom is being called carbocation. This carbocation now attracts the bromide ion with the negative sign. That's the electrophile. The nucleophile is going to react with the carbocation to give us our 1,2-dibromoethane. The reddish brown color of bromine is being discharged, indicating the presence of a multiple bond. 1,2-dibromoethane. The next example we see there, ethene plus bromine is going to yield us, ethene plus bromine in the presence of tetrachloromethane is going to yield R 1,2-dibromoethane. The reddish brown color of bromine disappears, indicating the presence of an unsaturated hydrocarbon. The next reaction we're looking at is addition of bromine or chlorine water. The halogens dissolve in water, forming hydrohalic acid. For example, we have bromine reacting with water. It's going to give us hydrogen bromide plus a hydrohalic acid. The bromic acid is what is known as bromine water. Alkenes react with halogen water or hydrohalic acids, forming alcohols. That is, it forms haloalcohols. Like you can see from the reaction below there, we have an arrow moving from the double bond of ethene there, that's the double bond of an alkene, to the positive charge of bromine. When bromine water is being hydrolyzed, bromine owns the positive charge, while the hydroxy ion owns the negative charge, and it's going to give us our bromoethanol. Alcohols which have a halogen are known as haloalcohols. You can see the compound there. Reacting further is going to give us 2-bromoethanol. The red-brown color of bromine water is discharged, indicating the presence of a multiple bond. Examples. In the case of chlorine water, we have, what we're trying to say here is, in the case of chlorine water, the hydroxy ion is going to be positive, while the chloride ion is going to be negative. And the attack on the double bond is by the hydroxy group. Like you can see from the example there, you have ethene reacting with chlorine water. If you can see, the chlorine water, hydroxy group obtains the positive charge, while chloride ion obtains the negative charge. Is going to give us 2-chloroethanol. That's it from the compound. You see it from the reaction, 2-chloroethanol. The next reaction we are going to look at is addition of sulfuric acid. Alkenes react with concentrated sulfuric acid, forming alkyl hydrogen sulfate. As alkyl hydrogen sulfate. If this alkyl hydrogen sulfate is boiled with water, alcohol is formed. We say they react with sulfuric acid, that is concentrated sulfuric acid, to yield alkyl hydrogen sulfate. Like there, you see the end product there is ethyl hydrogen sulfate. Now, if this ethyl hydrogen sulfate is boiled with water, alcohol is formed. See now from the reaction there, that is the ethyl hydrogen sulfate reacting with water and it is being boiled. It's going to give us ethanol plus sulfuric acid. We've come to the end of our lesson for today. In our next class, we're going to look further into the reactions of alkenes. And then we'll be looking also, we'll start another class of aliphatic hydrocarbons, which is alkynes. Thank you and see you next class.